Hello all, welcome back. We are discussing about the deep convolutional neural network architectures, and now we'll be discussing about the VGA16. This VGA16 is an acronym for Visual Geometric Group from the Oxford University, and this network comes with 16 layers proposed by the Visual Geometric Group. And this 16 layer contain the trainable parameters, and there are other layers like Maxwell. And this architecture was first runner-up of Visual Recognition Challenge 2014, that is ILSPRC 2014, and it was proposed by Karen Simoyan, Andrew Zisserman on a paper, Very Deep Convolutional Neural Network for Large-Scale Image Recognition. And we can see here the architecture of VGA16. Here we can see three like the blocks are discriminated by color, and we see some blue, red, pink and green. Here all the blue rectangles represent the convolution layers along with the nonlinear activation function, which is rectified linear unit ReLU. And there are 13 blue and the five red rectangles. These red rectangles represent the max fooling, and there are 3 green rectangles which represents the fully connected plus ReLU. This green color represents the 3 fully connected layers together with the ReLU. And so we can see here there are total number of layers is 16, of which 13 is for convolution layers and 3 for the fully connected layers. Thus the name is given as the VGA16. As the output, we have softmax layer having 1000 outputs per image category in the ImageNet dataset. And in this architecture we have started with a very low channel which is of size 64, and then it gradually increases by the factor of 2 after each max pooling layer until it reaches the 512. And here is the flattened architecture of VGA16, and here we can see like it starts with the depth of 64 and it finally reaches to the 512, and we can see the input image is of size 224 by 24, and before it reaches to the fully connected layer, it is the size is above 7 by 7. And we can see this architecture is quite simple. It has got 2 contiguous blocks of 2 convolution layer followed by the max pooling. We can see in the first and second, those are the contiguous blocks, which is followed by 2 by 2 max pooling, and another 3 contiguous blocks of 3 convolution layer followed by the max pooling, and at last we have 3 dense layers or 3 fully connected layers. And as compared to the AlexNet, this VGA16, like here all the convolution kernels are of the uniform size with the stride of 1, and in AlexNet it has a convolution kernel of variable size like 5 by 5, 3 by 3 and even 11 by 11. And though AlexNet uses multiple kernels of different size, the realization of every convolution kernel of the different size can be done by using 3 by 3 size kernel. Like if we are doing convolution with the 5 by 5 sized kernels, this 5 by 5 size can be realized with the 3 by 3 size kernels, and which reduces the computational complexity. And another one we are about to discuss is the GoogleNet, and as VGA16 was the first runner-up of ILSPRC 2014, This GoogleNet is the winner of that year competition. And in GoogleNet, the basic building block of the GoogleNet is the inception model. And so we'll be discussing about the basic building block of inception. And while talking about the BGSNet, the basic building block was the block of convolution layers of very small filters sizes, like it was of 3 by 3. And if we look at AlexNet, it had a variable filter size starting with 11 by 11, 5 by 5 filters and 3 by 3. So in case of inception modules, it incorporates with both this concept, says that every layer has all possible filter sizes. So they build a block of convolution. They build a convolution block which had multiple filter size. Here we can see, and this is called the inception module in the naive version. This is the inception module of the naive version, and this is the basic block of the inception module, which is known as naive version, and where we can use we can see the feature map from previous layer, and we have 1 by 1, 3 by 3 and 5 by 5 filter, 3 by 3 convolution and 3 by 3 max pooling. Also, and 3 by 3 max pooling is also applied to the feature maps, and output of each of them are taken and concatenated. Like we can see, filter concatenation means the output are the concatenated. And however, doing this operation, like doing the convolutions with different filter, especially with the 5 by 5 convolution, 5 by 5 size kernels, a problem of the complexity arises. And as this process consists of filter of size 5 by 5, the computational requirement increases. So in order to overcome this problem, the depth of the feature map is reduced by using 1 by 1 convolution. As we have discussed in our previous class, we use 1 by 1 convolution. We can use 1 by 1 convolution to reduce the depth, and which ultimately reduces the complexity. So we will see how the 1 by 1 convolution decreases the complexity. So the inception model says that instead of using the filter size you want on the convolution layer or pooling layer directly, we can use 1 by 1 convolution to reduce the dimension, and then we can implement 5 by 5 filter with the required depth. So let us see the difference of convolution, a computational cost on using 1 by 1 and with the 5 by 5 directly. Suppose we need to perform the 5 by 5 convolution here, and here we have a feature map of 14 by 14 and with the depth of 480. From this feature map, we want the output of 14 by 14 and say the depth is 48. Depth of the, say, like it's the depth is 48. Now we have here the 48 filters, like here we have got the 48 filters, and because the output has 48 channels, so we need to compute 48 by 14 by 14 by 48 number, and for each of them we need to do this many multiplication. Like we need to do this much multiplication, and which is 5 by 5 by 480. So the total number of multiplication we need is the number of multiplication we need to compute each of the output value times the number of output values we need to compute. So, and if we multiply all these numbers, this will be equal to 112.9 millions. Like we can see here, the total number of multiplication is the total number of output values, which is 14 by 14 by 48, into the total number of multiplication needed to compute the each output, which is 5 by 5 into 5 by 5 into 480. And here we can see the total number of multiplication needed is 112.9 millions. So if we think about the complexity, like even in the present computer, this much number of multiplication just to perform this 5 by 5 convolution is very expensive, or it's very computationally, this is computationally very expensive. So we need to go for the some alternative. So when we perform the 5 by 5 convolution in two steps, like in the first reducing the depth by 1 by 1 convolution, and 5 by 5 convolution with the desired depth size, this requires this much number of multiplication we can see here. And the first step, the total number of multiplication for 1 by 1 is here we can see that 14 by 14 by 16 into 1 by 1 into 480, which is equal to 1.5 millions. Like this is the total number of output values here. This first one is the total number of this 14 by 14 by 14 into 14 into 16. This is the total number of output values, and 1 into 480 is the total number of multiplication needed to compute each of the output. And with this we get the 1.5 million number of multiplication. And in the second step with 5 by 5, similarly we get the 3.8 million of the number of multiplication, and total number of multiplication required is the 5.3 million. So if we compare this much with the previous one, which is 112.9 million, then this 5.3 million is very less as compared to this. So with the use of 1 by 1 convolution, we can get the reduced complexity, or the computational complexity can be reduced using this 1 by 1 multiplication. So here is the inception model with the dimension reduction. So as we use this 1 by previous, as we have the previous layer, and from this we get 1 by 1 convolution, and then finally we perform the 3 by 3 and the 5 by 5 multiplication, and finally we concatenate the output of this, like we have 3 by 3, and then we also perform the 1 by 1 convolution, and then finally we get the filter concatenation. And this is the architecture of the GoogleNet or Inception. Here we have got input, and finally we get the output, and it consists of different number of inception blocks or inception modules. Here we can see that the GoogleNet has total 9 such inception modules stacked linearly, and total 22 layers deep, and 27 including the pooling layers, and it uses the global average pooling at the end of the last inception module. As with any very deep network, it is also subject to vanishing gradient problem. So to prevent from the vanishing gradient problem, the middle part of the network, like at the middle part of network, the authors introduced two auxiliary classifiers. The purple box we call here, like here we can see two auxiliary output in the middle of this architecture. and they essentially applied softmax to the outputs of the two inception modules and computed an auxiliary loss over the same levels, and the total loss function is weighted sum of the auxiliary loss and the real loss, and the weighted value used in the paper was 0.3 per for each auxiliary loss. So the loss function is calculated by considering the auxiliary loss as well. So this was about the inception, and it has got the different versions. So in inception version 2, it reduces the representational bottleneck, and the intuition was that the neural networks perform better when the convolution didn't alter the dimensions of the input drastically. So reducing the dimension too much may cause the loss of information known as representational bottleneck, and using smart factorization method, convolution can be made more efficient in terms of computational complexity. Like here what it has done is they factorize the convolutions of filter size of n by n. Suppose if it is n by n, then this n by n is factorized into 1 by n and n by 1 convolutions. Like suppose we have here, like it is n by n, it is factorized into 1 by n. Suppose for n by n, it is factorized into n by 1 and 1 by n. Like we can see here with the 3 by 3 example, the convolution is equivalent to first performing 1 by 3 convolution and then performing 3 by 1 convolution in the output, and then they found this method to reduce 33%. Like it is more cheaper, 33% more cheaper than the single 3 by 3 convolution. Like we can see here, okay, and the filter banks in the module were expanded to remove the representational bottleneck as well. If the module was made more deeper, instead of there would be excessive reduction in dimension, and then the loss of information. So here what it does is like it just factorizes the filter so that the complexity can be reduced. Okay, like here what it has done is like for the factorization, like for the factorization like it has done to factorize 5 by 5 convolution. This 5 by 5 is convolution is achieved is realized by two 3 by 3 convolution operations, and this it has like here, although this may seem counterintuitive, a 5 by 5 convolution is 2.78 times more expensive than the 3 by 3 convolution. So what it does is it stacks two 3 by 3 convolutions, and which in turn will reduce the complexity and boost the performance. So this here we can see this n by n, the factorization of n by n can be seen, like can be realized with in terms of 5 by 5, which is this 5 by 5 is reduced is factorized into 3 by 3, and even this can be realized with even the complexity can computational complexity can be reduced by performing like for 3 by 3 we can perform 1 by 3 first and then 3 by 1 convolution, and which in turn reduces the complexity. And another another widely used and the most another popular architecture in the deep learning is the ResNet, which is short form of the residual network, and it is a specific type of neural network that was introduced in 2015 by Kai-Ming He, Xiangyu Chang, and Sang-Xing Ren and Jian Sun in their paper Deep Residual Network for the Image Recognition. And the ResNet model were extremely successful, and it won the first place of ILSPRC 2015 and the classification competition with the top error rate of 3.57, and it also won the first place in the COCO 2015 competition. And ResNet, the need of ResNet is mostly in order to solve some kind of complex problem. The intuition behind the ResNet is like the motivation behind the ResNet is in order to solve some complex problem, we usually stack some additional layers in deep neural networks, and which results in the improved accuracy and the performance. And the intuition behind adding more layers is that like these layers progressively learn more complex features. For example, in case of recognizing image, the first layer may learn to detect edges, and then the second layer may learn to identify the textures, and similarly the third layer can learn to detect the object, and so on. So in order to in general we assume that with the increase of layer, or with the increase of number of layers, or more we increase the number of depth, more we make the network depth deep, the accuracy gets increased. But it has not but it has been found that the maximum threshold for the depth with the traditional convolutional neural network model, like we cannot increase the number of depth, or we cannot make the network more deep beyond some threshold. So we can see here a basic plot, like in this plot we can see the error percent on the training and testing error with the 20 layer and 56 layer. Here we can easily see that the error rate percentage for 56 layer is more than the 20 layer network in both cases of training data as well as the testing data. We can see here that 56 with the 56 layer and the 20 layer, the training error rate is high as compared to the 20 layer. So in case of 56, like it is the training error rate is high, and training as well as test error percentage is high. So we can see that the error percent for 56 layer is more than 20 layer network in both cases of training data as well as testing data. This suggests that with the adding more layer on the top of the network, its perform degrades. So the reason behind this is like as we go more deeper and deeper, the vanishing gradient problem occurs that we have discussed in our previously. So to get over this problem, the ResNet paper proposes something called the skip connection. So here is the here we can see like these connections are basically an identity mapping. Here, like this is the input. Here we can see the identity mapping. They provide alternate path for the gradient flow and makes the training possible. And for ImageNet challenge, they managed to create up to 152 layers of network. Like by adding this kind of identity map, they had created up to 152 layer network. As we have seen here, like the problem occurs in 56 layer, but with the help of this identity map, the authors had created up to they had added up to 152 layers. So the core idea of restaurant network is like, we know that the shallow network seem to work well, so we use we can see that the shallow network, as we have seen before with the 20 layer, with the comparison between 20 and 56 layer, this 20 layer, like this shallow network, gives us the better performance. So what they did was like they use the weights of shallow networks to construct a much deeper network, and wherever they find the gaps, or whenever there is a gap, they just do the identity connections, which means like here identity connections means we can see here two convolution layer, and it takes a bunch of input, bunch of feature map x, and it has the output hx. And here we can see the output hx is equal to fx when there is no identity map. But when we add the addition, when in the addition to this output, what is also done is like we have here the skipping two layers for the convolution layer, and the input of convolution layer 1 is copied to the output of the convolution layer 2. Here this is the convolution layer 1, convolution layer 2. This input of this convolution layer 1 is copied to the output of convolution layer. Now the output becomes like hx is equal to fx plus x. So now instead of learning just hx, the network will learn the residual, means the basically we are trying to learn this fx is equal to hx minus x. So in the worst case scenario, if we don't learn anything, or the weights are not updated, or the weights are zeros, or the when there is no or it is very small or zero, then this fx will be 0. This fx gets 0. Suppose this, when this fx is 0, means nothing is learned, or all the weights are 0. So in this case the output will be hx is equal to x. So at least in this case it will learn at least x. So that's the idea, just at least learn or learn something or x, or in this case the gradient, the flow of gradient does not stop, or the gradient of flow happens. So in the worst case scenario, the worst case scenario means when nothing is learned, or fx is equal to x. Even in the worst case scenario, the flow of gradient isn't stopped, or there is some flow of gradient, or something is learned. So suppose in the best case scenario, the additional layer of the deep neural network can better approximate the mapping of x to the output h, then it's in the shallower counterpart, and reduces the error by significant margin. So, and thus we expect ResNet to perform equally. In worst case, it will perform equally to the shallow network, but in best case it will perform better than the plain deep neural network. So here they have shown, like we can see here, with the 34 layer plain network architecture, and it's inspired by BGG19, in which the shortcut connection is added, and these shortcut connections then convert the architecture into the residual network as shown in the figure below. Here we can see like here it has got the architecture like same as BGP, but the difference is like it adds the shortcut or it adds the skip connection. And after adding the and they compared the result here, and we can see here using the ResNet has significantly enhanced the performance of the neural network with more layers. And here is the plot of the error percent with the comparing it with neural networks with plain network layers. Clearly we can see here the difference is huge in the network with 34 layers, where ResNet 34 has a much lower error as compared to the plain 34. Also we can see the error percentage of plain 18 and the ResNet 18 is almost same. Like we can see here, like we can see this is the plain 34 and plain 18, and like we can see in case of plain 34 the error is higher as compared to the plain 18. Like here the plain 34 means it is more deeper but without any skip connection, so only the network is made deeper. So here we can see same as in our previous example here with the increase of depth, the error gets increased. But in case of ResNet, with the help of ResNet or with this help of skip, we can see that as the depth increases, like here this red line for the ResNet 34, with more depth the error is lower than the 18 layer. Like in the case of 18 layer, this is also 18 ResNet 18, which is like as the depth increases the error is decreased. So this shows that the ResNet gives, with the help of skip connection, we can get the better performance. Even we increase the depth of the depth of the network, or we as we make the network more deeper, the performance gets even improved with the help of ResNet. So it's all about the different architectures, and there are lots of architectures which have been developed until this date. You can find lots of architectures for the image classification problems. So I will not be covering those, but we will be seeing some other computer vision problems in our subsequent classes. So you can find other architectures, but the foundation or the basic building block of all these architectures are almost from those we have studied so far. So you can find those architectures, and if you are interested, and in our subsequent classes we'll be discussing about the other computer vision problems, which also where we use deep learning method to solve those problems.